Today, I want to talk about functions of two variables, which we have talked about already, but we want to be more specific about bringing some chapter 14 and chapter 16 stuff, that is derivatives and integration, into our thinking. I want to bring this stuff on board early because we already have these ideas in our heads. We've already seen this kind of stuff in Calc 1 and Calc 2. So let's start with a function. Let's say z is equal to fx. And let's suppose that we have this set of values for z. Now, the things that we do when we're doing calculus, first we describe stuff. We talked about that last week. Second, we do derivative stuff. Yeah, 14. And third, we do integral stuff, chapter 16. Let's see what we did with derivative stuff with this table of values. So derivative stuff means we could do is approximate the derivative at any one of these points using the given information. So let's suppose I wanted to approximate f prime of 3, the derivative at 3. So we know that f prime of 3 is going to be the slope of the line tangent to the function at 3. So this is what we know about derivatives. F prime of 3 is the slope of the line but f prime of 3 is going to be the slope of the line tangent to the graph of f of x when x is equal to 3. Furthermore, we know that the slope is change in, well, in this case, z, change in z divided by change in x. We know that slope is rise over run. We get to describe two different numbers with 1 because we're just going to make a ratio out of it. And in this case, rise will be our change in z, and our run will be the change in x, just like it's always been. So looking at the point where we have 320, the next piece of information that we have is at 640. So one way to calculate the slope is just to calculate the 2 points that are right next to each other. So I could calculate the slope . I could say from 3 to 6, the function increases from 20 to 40. That's an increase of 20. So the rise is 20. And 3 goes up to 6. And so x, the change in x is a positive 3. So we could approximate the slope as being 20 over 3, or 6 2/3. We can also calculate the slope using the information before 20 because we have information on both sides of 3. We can say what happens from 0 to 3. So we ended up at 20 and we started off at 10. We ended up at 3 and we start off at 0. So 20 minus 10 is an increase of 10 divided by 3, an increase of 3. So we have a slope of 3 1/3. Not a very satisfying range. How much is this going to cost me? Somewhere between $3.33 and $6.67. If those values are the ones digit in the price of the part, it's going to cost tens of thousands of dollars, we won't really care. But if we're in a store and we've got a $10 bill, we want to know if we can afford it. Or if we have a $5 bill, we want to know if we can afford it or we can't afford it. But our information is not very high of a resolution. But if we want to approximate a value, that's what we would do. That's the information that we have. We can say the slope is somewhere between 3 1/3 and 6 2/3. We shouldn't have expected a lot of accuracy because Z is changing quite a bit. For these, we got these big leaps of X from 3 to 6. And Z seems to be changing quite a bit. So we shouldn't expect a lot of precision at this point. This is like Game Boy level precision as far as the graphics go. You can see each individual pixel on the screen. That would be an example of derivative stuff that we could do with this information. Very limited information about this function of just one variable. Other things that we could ask. We could say approximate the integral from 0 to 9 of f of x dx. There's another case we're going to be able to write lower and upper estimates of our definite integral. We want to find the area under the curve of f of x and above the interval from 0 to 9. To do that, we're going to think of the interval, sorry. We're going to think of the definite integral as an area. We're going to find the area under the curve of f of x and above the interval from 0 to 9. Since we are calculating area, the only formula we ever need for area is length times width. Whatever else you think about area, area is always length times width, because everything is just a bunch of rectangles. That pi r squared circle, that's just a shortcut. That's just length times width applied to a circle. 1/2 base times height for a triangle. That's just a rectangle, but in half. It's a shortcut to find the area using length times width a bunch of times. Similarly, trapezoids, parallelograms, all that stuff. Area is length times width. Not area of a what? Area is length times width. How long something is multiplied by how wide it is. The reason that we have to use integration is that our stupid length keeps changing. In this case, our length is just 4 different values. We have to do definite integrals when our length is changing, not just discretely like we have up here, but continuously. But since we only have 4 discrete values, we're just going to find an area. We're going to think of this area. This is going to be the area under graph of, and above area under the graph and above the interval. And we are going to approximate this area using 3 rectangles. We're going to imagine this area as just being 3 different rectangles. So here are our three rectangles. When x goes from 0 to 3, then 3 to 6, and then from 6 to 9. There's our three rectangles. There's a reason that I was not picking 3. I was going to say, oh, make it 5, 0, 5, 10, 15. And then what goes to happen? I'm going to make 3 rectangles instead of 4. You had a professional teacher, this kind of thing wouldn't happen. But instead, you're stuck with me, so there you are. There are 3 rectangles, and the width happens to be a delta x of 3. And we're going to use the values of z as the height of each of those rectangles. Those are our widths, and down here are going to be lengths. Down there is going to be our lengths of rectangles. So that first rectangle where delta x goes from 0 to, or the x goes from 0 to 3. There's our width of 3. We have to pick a value of the function for the height. The value of the function is at least 10, so I can get a lower estimate of that area by using 10 all the way across. We see that the value of the function is at most 20, so we could use 20 as an upper limit for the length and come up with 2 different estimates. So I'll calculate the lower estimate. By taking my delta x of 3 as the width. And then that first rectangle is at least a height of 10. In my upper estimate, I'm going to have the same delta x of 3, but I'm going to say that that first rectangle is at most 20, and that'll give me an upper bound on area. There's my width 3, but that first rectangle is at most 20. Now I move on to the next rectangle that has a height of at least 20 and at most 40. So for my lower estimate, I'm going to pick 20. And for my upper estimate, I'll pick 40. And then we'll do the same thing with the 40 and the 70. So the definite interval from 0 to 9 at f of x, the actual area under the graph and above the interval from 0 to 9 is at least 210. And at most 7, 11, 12, 13, 390. Our estimates are pretty far apart, but we have a pretty low resolution sample of our data. We're just trying to get approximations, and I just want to start. I want to start by going on looking at the technique, how we make a calculation, so that we can upgrade our function of 1 variable to a function of 2 variables. And if I could make a 3-dimensional table, we can upgrade that to a function of 3 variables. Where I can have x, a function of x going one way, a function of y, and then a function of z. If I could have like a 3-dimensional table. But I can't, I'm stuck in this primitive 2-dimensional thing. How's everybody okay? It's crazy that I would look at this as primitive. When in my lifetime, we have gone from chalkboard having very expensive projectors and chalkboards just going away. There have been entire methods of media storage that have come and gone in my lifetime, like while I've been alive. Cassettes were around, like, does anybody know what cassette is? Cassettes were around before I was born, but there was another cassette that wasn't around when I was born. That's the VCR. Everybody know what a VCR is? Yeah, you've seen pictures of them in history books, right? Where I actually used to record entire movies on magnetic tape. This is why every time you watch like concert footage from the 90s, it will always and forever look terrible. There's nothing that can be done to fix it. It is permanently bad because we started videotaping them. Before that, it was a lot of effort. We had to film stuff, but if you caught something on film, you had a chance to make it better. Not with an old film print, but take an old film print, remaster it, and make it better. You just can't do that with videotape. The information is just gone. There's a plus C at the end that we'll never get back. That's why everything from the 90s is just going to look like trash forever. You know what I mean? All right. CDs. Does anybody still listen to CDs? Pretty much have come and gone in my lifetime. Is that? You have a whole truck. Yeah, now it's a premium, right? You still have to set some more listen to that. Now they're saying, whoa, that's gotta be special. Yeah, vinyl never really goes away. Vinyl always is, I think vinyl is always gonna have a place in the human psyche. I think vinyl is here to stay. But there's nothing that CDs bring to the table anymore. It's a digital copy. There's no one's going to be nostalgic for CDs. You know what I mean? What's that? Right. Because physical copies of things are going away. So, anyway. We like to think it's a case of you either pivot to the new stuff or you pass away, your business just goes away. But clearly that's not the case. Because the other option to that, it's either you pivot to the new medium or your business goes away. Like ask Kodak how that went. It's like, oh, this is just a passing fad. And no one said, you realize, and they were like, well, look at how bad the resolution is. But you realize that computers are going to get better and faster. Kodak, and Kodak's like, oh, ha, 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 no. And then they're like, oh, ha, ha, oh, bye. Well, he didn't pivot to the new thing. They also didn't exercise option 3, which is make sure that there are laws in place so that your business will never go away. Right? So the oil company was like, oh, electric cars? No, we'll not have any of that. Yeah, they are now. They are now. But look what it took for the established car companies to start making electric cars. It took a whole other company to come along and become really popular. Tesla had to come along, otherwise electric cars, the Mach-E wouldn't exist. The Chevy Bolt wouldn't exist. Chevy already made an electric car back in the 90s, the EV1. And they killed it because they're like, oh man, if we actually built an infrastructure to support this, everybody will want it. Not like the gearheads that care about V8 engines and supercharging and turbos and all that other stuff. All that stuff would still be there, but it would have been pushed into a niche market. You know what I mean? If you don't believe me, look how popular crossovers are. Car enthusiasts have to know that their favorite thing is going away. And we don't really have power to stop. You know what I mean? Anyway, what are we talking about? Right, higher resolution. And the extra thing that comes along with this We had to get rid of things like chalkboards, even though the chalkboards themselves are cheap or expensive. The chalk was really cheap. If this was a chalkboard, and all I was using was a chalkboard, 12 cents of chalk would pretty much carry me through the semester and all 3 on class. No problem. Just one box of chalk. It'd be like a pen. You'd never get through the whole thing. You'd use it before you could finish. But now the chalk actually creates a danger in other technologies we have in the world. Right, just like smoking. All right. Let's upgrade this function to a function of 2 variables and see these same calculations show up. Let's suppose I'm going to still have in the x direction here are values of x. Now let's take a look at values of y. So here are our values of f of xy. So in this table, if I wanted to calculate, say, f of 6, 5, when x is 6 and y is 5, z is 38. That's how we're reading what's going on. So we want to ask the same questions that we had before. What's the derivative question here? How can we approximate it from the table? What's the integral question here? How can we approximate it from the table? We need some notation for this. So if I write f sub x of, let's say, 0, let's just use this, 6, 5. So when I write f sub x of 6, 5, this is going to be my derivative in the x direction. I didn't have to make this distinction before because all we had was one direction. That's a horrible thought. There's only one band. I'm not familiar with the catalog. I should be making fun, but the idea of just having one band is kind of fun. I didn't have to make a distinction between x and y before. I just had to write f prime. But now I have to distinguish between the change in z in the x direction and the change in z in the y direction. So this is going to be the change in z in the x direction. That's what the sub x means. We can't use prime. We've got to distinguish between changing in the x direction and changing in the y direction. So this sub x that x is our prime, but it's for x because I got 2 directions. So for this calculation, we're going to see how much z changes when x changes. So that's going to be these changes or these changes. So I can either get an upper estimate by saying 68 minus 38 divided by 9 minus 6. Or I can take 38 minus 18 over 6 minus 3. So I either have an increase of, it's going to be 30 over 3, so 10, or 6 2/3. So z is increasing by somewhere between 6 2/3 and 10 in the x direction at the point 6, 5. We're asking derivative stuff. Derivative stuff is just slope stuff. If all we have is 2 points, we find the slope between 2 points. Same as we've always done. But just like Skywalker's, there is another Fy at 6, 5. And for this, we're going to calculate the change in z divided by the change in y. So once again, f sub y is like f prime, but we have to specify whether it's the x or the y direction that we care about. And we can either go from this 38 to 36, go this direction, or we can go the other direction. But it looks like in the y direction, things are changing linearly. We're decreasing by 2 every 5 units. So we can either do 36 minus 38 divided by 10 minus 5 for a negative 2/5, or 38 minus 40 divided by 5 minus 0, also negative 2/5. I spelled 5 wrong. Same thing. Notice I got the same if I calculated before or calculated after. This is because when I set up this function in the y direction, I made a linear function. All I did was subtract 2 every 5 units in the y direction. So we're not surprised that this came out the same. Any questions? Now, the other thing is going to be, what is the area under the curve? Well, that question, since we don't have a curve, we have a surface, and we don't have an interval, we have a region. The question has to be modified. What is the volume under the surface and above the region? So x is going from 0 to 9, and y is going from 0 to 10. Remember what we're calculating here. The integral is just multiplication, but one of the factors is variable. And in this multiplication, we're taking f at xy, height above a point xy, multiplied by area, dy times dx. The integral symbol is just telling us what values of x and y to plug into this calculation to get the thing that we want. This is the same thing that we did before with the interval from 0 to 9 and f at x. We're taking the f of x times dx and evaluating that at all the values between 0 and 9. We've just got 2 here. We've got 0 to 9 on the x, 0 to 10 on the y. Any questions? It does. So notice that the other thing is, I put the dy, in the dy dx, I spelled this part dy dx. This is because the y values that I'm plugging in are 0 to 10. And so this first, this integral on the right side has to correspond with the y. Yeah, so we're not reading left to right, we're reading inside out. So the 0 to 10 corresponds to the dy. This is y equals 0. Y equals 10. And the 0 to 9 is the x. That one goes on the outside. So rather than a first and a second integral, we should talk about the inside and the outside. So this says x equals 0, the x equals 9. We want to do the same thing. I want to find a lower and upper estimate for a bunch of rectangles. But our estimates are going to be a little, instead of intervals, are going to be small rectangles. Let's take a look at this first piece of information we have. We got the point 0, 0, we got a 10. We look at a top-down view. At the point 0, 0, we have a 10. At the point 3, 0, we've got a value of 20. At this point down here, this is the point, let's say, when x is 0 and y is 5, we're at 8. And down at this corner, at the point 3, 5, we've got a value of 18. These are the four corners above that first rectangle when x goes from 0 to 3 and y goes from 0 to 5. So I'm going to take this area and multiply by the lowest height that we have available. It looks like 8. So our lower estimate for this rectangle only is going to be 8 times the area. I've got this area. The area is going to be 3 times, put everything right in the middle, I thought. That'll be fine. So the area on the floor is 3 times 5 or 15. That's the delta x times the delta y. And then for the height, I need a lower estimate. So the lower was going to be an 8. Then in the other corner at 20, that's going to be the upper bound for this rectangle, or for the height above this rectangle. So for my lower estimate, I'm going to take my area of 15. And I'm going to use this first rectangle's height of 8. And for my upper estimate, I'm going to use my area is 15. And for this first rectangle, the highest value is 20. Now we just have to go each rectangle that has an area of 15, find out which one is lower and which one is upper. If I start drawing more rectangles, here's going to be the 0.60, and this will be the 0.65. And I'll have two more values here, a 40 and a 38. So the next four, the lower estimate is going to have an 18, and the upper estimate will have 38. Or sorry, 40. I was on the wrong word. But all we're doing, since this is an integration, it has to come from multiplication. Now we're just taking area, the 15, times the height to create volume. This is going to be the volume under the graph of f of x, y, and above the rectangle, 0 to 9 on x, 0 to 10 on y. Any questions? Everybody okay? So I have to ... I'm the only one in the room that gets to use ... at the end of a problem. Y'all don't get to be like, oh, and then there's some more stuff. The rest is left up to the reader. I always get it wrong, so don't start to do that. So only I can say, oh yeah, I do the rest. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.